welcome everyone to the next session of Introduction to Biomedical Optics. Today we will talk about a very important part, that is we will start to develop a construct, a mathematical construct for quantifying the coherence. In the last class we talked about loosely of how to understand coherence as an abstract topic which could be used as a parameter to differentiate whether it is a temporal coherence or spatial coherence, and that we can use it for many other applications like spectral contrast imaging, or to get the gravitational waves, to acquire the gravitational waves that we discussed. Now in today's session we will try to understand the mathematical reasoning of how to quantify both the temporal as well as spatial coherence. Before starting to understand what is coherence, what we will do is we will try to understand what is a light packets, right? So how does the light is being emitted? Now when we talk about any particle, it has it has many bands in which what happens is that you have the electron at a very higher band and it actually jumps from a higher band to a lower band, okay, and in that process it actually emits a photon of light. Now for example we take about for example of a neon, okay, so this band gap, the energy that it is able to jump is about 1.96 eV okay, and if you talk about what is 1 eV, so 1 eV is around 1.602 times 10 power minus 19 joules, okay. So now so if you talk about what is the jump in the terms of joules, you can actually just multiply 1.96 eV into 1.602 times 10 power minus 19 joule, and you will find that that jump, that delta E, is nothing but about 3.13 times 10 power minus 19 joules, okay. So that is the jump that the electron comes, and because of that jump it actually converts into a photon. So it actually releases a photon of a particular wavelength. Now after this we also want to understand what is the wavelength of the photon that it is emitting, right. So that is nothing but given by the Planck's equation, that is H equal to H cross into delta E is equal to H cross into nu, where H cross is the Planck's constant and nu is the frequency. Now from this you can calculate your nu, which is equal to delta E by H. So we know what is delta E, that is around 3.13 times 10 power minus 19, and H cross is nothing but Planck's constant, that is 6.62 times 10 power minus 34. So if you do that, you get it, the frequency of the photon which is emitted is around 4.72 times 10 power 14 hertz, okay. So this is the emitted frequency of the photon. Now once we know the frequency, we also want to know the wavelength of the emitted photon, because the wavelength is kind of more intuitive rather than talking about the frequency, right. So now we know what is the relationship between the photon and the wavelength and the frequency. So that is nothing but your C equal to nu lambda, or C equal to f lambda, right. So here nu is more used as compared to the f. So you want to find the lambda, which is nothing but speed of light divided by the frequency, that is 3 times 10 power 8 meter per second divided by nu, that is you already calculated out 4.72 times 10 power 14 hertz. So hertz is nothing but 1 over second. So if you do that, you find that your wavelength is nothing but about 635.5 nanometers. So if you calculate this out, you will get that the wavelength of the photon is around 635.5 nanometers. Now you have the frequency, you have the wavelength. Now you also want to know what is the time period of this wave, right? So now, what would be the time period? Time period is nothing but 1 over nu, and if you do that, that is 1 divided by 4.72 times 10 power 14 hertz. So that comes around 2.11 times 10 power minus 15 seconds. So you can see that we are dealing with such a short duration of time period of a particular photon. Now the photon that we are talking about, that photon is a kind of a wave. Okay, so whenever we see a particular photon to be released from a particular atom, for example, this is that atom, and there is electron which is moving from a top band to a bottom band and gives a photon. So it gives in the form of packet. So it's known as wave packets. Okay, so wave packet looks something like this. Okay, so now we know what is your delta t. So delta t is nothing but the time between two peaks, right? So it could be this peak and this peak, right? So this could be the t, and that we calculated it out as around how much it was around. Yeah, it was around 2.11 times 10 power minus 15 seconds. So this is the time period that we are talking about, right? So it's kind of very small, right? Now this release of photon, it could be happening spontaneously or stimulated, right? So it can, both of the type of emission could actually occur. So what you will see that as a function of time, you will see that sometime you will see that the wave packet would be, one wave packet would be generated, then after some time one more wave packet would be generated, and then one more wave packet would be generated. Okay, so this could be one of the case that could happen. Another case that could happen would be that the time distance, the time between the generation of two wave packets could be like very close by. So there would be a superposition of the wave packets, and what you will get is something like this. Instead of a wave packet which are spaced apart, you will actually get that it is something like this. Okay, so here there are all the three or five all the five of the wave packets are actually superposed together, and here you can see that this is the time where it is coherent, right? So coherent means in this case it would be like it sustains its own wavelength, a specific wavelength, for a significant period of time. So that is kind of known as we talk about now, temporal coherence. So now we actually trying to talk about temporal coherence in our first session. In the next session or next to next session, we'll talk about the spatial coherence, right? So this we can tell that from this period on over here from this period over here to this period over here, it is having a good high temporal coherence. Okay, so so we actually can define coherence in terms of the the wave packets. Okay, so consider the single wave packet has the time duration of t naught. Okay, so here there are three definitions that we are discussing. First is the t, as you can see over here. So this t is nothing but the time period of the wave packet. This t naught is the time complete time in the complete time duration of the wave packet, while tau c is the time duration of the complete superposition of the multiple wave packets, where it sustains a particular pattern, right, or a particular wavelength in this case. So if, for example, from this point over here to this point over here, it would be absolutely or kind of perfectly deterministically, it would be 635 nanometers, right? It will not shift its particular wavelength. Okay, now based upon this values of tau c and tau t naught, we can actually tell whether the waves are coherent, partially coherent, or incoherent. For example, there could be a case like where there is a tau c is approximately equal to T naught, okay, where tau c is approximately equal to T naught. In that case it is called as incoherent, okay. Now which means that that is the first case, right, where tau c is nothing but equal to approximately equal to T naught. Now there could be another case where tau c is greater than T naught, okay. So in that case we can say that it is partially coherent, okay. And then the second case that we talk about is this the second case this we talked about over here, where Tc is far greater than T naught, tau c is far greater than T naught, and over here we tell that it is a coherent wave, okay. So we can say that it is significantly coherent. So this is the understanding of with respect to the generation of the photons, which is nothing but in the form of generation of wave packets, okay. Now let us understand, now if you want to quantify this or you want to measure this whether this light source that you have with you is actually coherent or not, what kind of detectors do we use? So we usually use something known as silicon photodetector. That is one of the example that we generally use. Silicon photodetector has p and n junction, and whatever photon it actually it reaches over there, it can actually absorb and convert into the flow of electron, and which can be converted into the measurable quantity such as current, okay. So let us again consider this wave packet, okay. And now this is the intensity, and now what we see is that this is the time period between the two peaks, okay. Now the time peaks, for example, we talk about we are using an helium neon laser, okay. We are using helium neon laser having a operating wavelength of 632.8 nanometers, okay. You can convert this into a frequency, and then you can convert into a time period, and that time period is nothing but, if you can calculate it, nothing but 1 over nu, that is 1 over frequency, right, and that is given by lambda by c, right, because nu c equal to nu lambda, okay, and t equal to 1 by nu, okay. And if you do that, you will find that the value of t comes about 2.10 times 10 power 15 seconds, right, similar in order of femtoseconds as compared as we have done earlier as well, right. Now when we talk about the detectors, because we want to detect this wave packet, when we talk about silicon photodiode, when you talk about silicon photodiode, it has a bandwidth, okay, of approximately about 1 megahertz. That is most of the generalized photodiode that we have, it can max go to a frequency of or it could actually reach to the frequency of 1 megahertz, right. Now if you want to see this delta t, that is how much quick it can actually detect, is around 1 divided by 1 times 10 power 6. So you can see that your delta t is actually 1 times 10 power minus 6 seconds. So it can detect up to 10 power minus 6 seconds, which is like very high as compared to 10 power minus 15. So almost in order of around 9 times 9 order of magnitude higher than what we actually want to detect. So we want to detect in order of femtoseconds, but actually what we can detect is in only in order of microseconds, right. So in that case, what we can do is that we can actually, rather than having the complete instantaneous fluctuation of your wave packet, we can actually go and work with the average of the wave, right. So let us see how can we actually work with the average. So any wave packet, again we talk about the wave packet again, okay. So this is the time, this is the intensity. So this can be defined as electrical field, where it is as a function of space and time. Okay. So this space and time, it could be r and t. R is a vector quantity because it x, y and z, and t is the time. Right. Now we can tell about its intensity. Okay. So intensity can be defined as a function of again r and t. Now this is the average intensity that we are defining. That is nothing but, now this is what is the definition of average. Okay. So when we talk about something like this, so this actually denotes average over a time which is kind of very, very large than capital T. Okay. Now this is the average intensity. Okay. So let me just write that this is a average intensity. Right. Now we also want to know what is a temporal average, right. So with respect to the time. So temporal average also we can define, and that is given as for example, if we have any function f of t, right, its temporal average can be given as f of t with these triangular brackets, and that is over a particular time, that is delta t. Okay. So that f of t, now this f of t could be in electrical field as well. Okay. So that is given by 1 over delta t, and that is given as 1 by delta t minus delta t by 2 to capital delta t by 2 f of t. Now I am just introduce one more t cap to differentiate the actual time with the newly developed time instances. Okay. So instead of actually working with instantaneous fluctuations of your electrical field, now we actually work with the average intensity, that is nothing but the square of your electrical field, and temporal average of your electrical field, that is nothing but 1 over delta t, that is the time that you take, and then from minus delta t to plus delta t, and then f of t dt. Okay. So we will use this definition to go ahead and to define the coherence, right. Okay. So now let us understand, like how do we define coherence, right. So what is a coherence? Okay. So coherence is again, it could be again differentiated in 2 points, okay, 2 characteristics as we have discussed earlier. So it could be having temporal coherence, or it could be having a spatial coherence, right. So we start with definition of the temporal coherence, and then slowly we will build up for the spatial coherence as well. Okay. Now when we talk about temporal coherence, what do we mean by temporal coherence? So it is nothing but a time period over which the wave is able to correlate with itself. Okay. So what now we are going to talk about is correlation, right. So correlation means I want to correlate apple with orange, right. I want, so if so there would be very low degree of correlation between apple and orange, right. Now I can correlate one apple with another apple, right. So that is another degree of correlation, right. So there will be some correlation that I will get, some, if I want to quantify between one apple to another apple, there would be some value of correlation that I am going to get. Now for example, I so if I am comparing one apple with another apple, then it is something you can call it as cross correlation, right. Now I can also compare a same apple with the day 1 of the produce, and then I compare it with another, the same apple with day 2 of the produce. Right. Then I can compare it with the day 3 of produce. Now this comparison between the same apple with at different time is actually known as autocorrelation. Okay. So when we talk about temporal coherence, we more or less talk about autocorrelation. So it's nothing but it's the same electrical field, but we correlate it with a time shifted uh, or delay of the same electrical field. Okay, for example, it is this particular electrical field wave packet, but it is now shifted with a particular time instant. So this shift is actually given by tau. Okay, so this tau is what we are going to see at what value of the tau would it lose the correlation. Okay, there would be some tau after some time that it will definitely not able to recognize its own self, right? We are shifting it, keep on shifting it, keep on shifting it. After some tau value, it will say that that it's not actually equal to the earlier wave anymore, right? So in when the tau is very small, then it can actually correlate. Somehow it can correlate. So at tau equal to 0, it would be the same as what it is actually your original electrical field. But as you go on increasing your tau, you will see that your correlation, your degree of correlation, just loosely put as degree of correlation or autocorrelation in this case, will actually slowly lose down as you increase your tau. Okay, so this is what you will try to see over the period of time. Okay. Okay, so now let us see how do you actually define this correlation. Okay. Okay, so now we define there is something known as mutual coherence function. That is the two different fields. So now I can define the mutual correlation function as gamma R1 T and R2 comma T2 is given as, this is the conjugate of R1 T1 with the this is R2 and T2. Okay. Now this is defined, mutual coherence function defined for which positions? So which positions? This is for R1 and R2. Okay, and it is observed at what? It is observed at T1 and T2. Okay, so this is how you define the the mutual coherence function. Okay, now when we talk about autocorrelation again, autocorrelation. So in the autocorrelation is the same position, right? So it's not actually two different positions, it's the same position. So it could be like R1 equal to R2, that is nothing but equal to Z. And in the in the time observed, it is nothing but T and then T plus tau. Okay. So now we can define this our mutual correlation function as a function of tau now, because that is only the thing that is changing, and then I can define it as, so now even the Z part it can be neglected, and I can just write it in terms of this one. Okay. Now this triangular brackets are coming because of the use of the average terms. Okay. Now considering the delay tau equal to 0, can you just think about what would be the value as we discussed some time back? It would be, what do you think would be the value? We just pause this video and just think about it. Yeah. So if you would think about, so it would be nothing but the tau is 0, so it becomes something like this. So when we talk about intuitively as well as mathematically, you will see that it is the same. So it is nothing but the intensity Okay, that is the highest intensity that you actually get. So this is nothing but this value that I was talking about, that highest intensity that you will get when you have the delay to be 0. But as you go on increasing this delay, you will see based upon that wave packet that we have, based upon that it will slowly die or it will stay constant. Okay. Now we never actually work with only the mutual coherence function, but we need to normalize it, right? So we don't usually work with absolute values, but we work with functions which are having maximum value as 1. Okay. So to do that, we actually normalize the mutual coherence function. Okay, to do that, now I will introduce a new function, that is small gamma as a function of tau. Okay, so that would be nothing but capital gamma as a function of tau divided by gamma, capital gamma as a function of at 0. Okay, that is your intensity, right? So now I can define it as E star okay, divided by conjugate of E into E of t, right? It's nothing but, if you want to write it in simple terms, is nothing but conjugate of E into the time delay with tau divided by I of t. Okay. Now this term after the normalization in the field of optics is known as complex degree of temporal coherence. Okay. So this is what is defined as a complex degree of temporal coherence. Okay. Now we at a later on we will actually find how you can define the temporal coherence, that time for the temporal. So how much time do you can we say that the wave could be coherent? Okay, so that is the tau c that we will actually define. Okay. Okay, so that's what I wanted to plan for this session. Okay, in the next session we will talk about how do we find the temporal coherence. Okay, so I will just summarize what I discussed today. So we first started with how is the generation of wave packet. So for a single atom, there is a movement of electron from higher bands to a lower band. It creates a particular wave packet of a particular wavelength, so that we can actually find it using the Planck's equation, and from there the wave packet could be generated at different time instants. So assume that wave packets are generated simultaneously, it can overlap with each other to give a very smooth pattern of your light source, and that would be, for example, a very monochromatic, a very deterministic, perfectly monochromatic light source, and that would be for a particular instant, and that instant is known as tau c. Okay, and that tau c will actually help you to find whether it is coherent or incoherent, right? So let me just enable this laser pointer, I think, yeah, good. Yeah, so this is the tau c, which actually we say that within this period the wave is or the light source is coherent. Now when we define for a single wave packet and for the superposition of wave packet, we can say that with if the tau c is approximately equal to tau naught, it would be incoherent. If it is more than T naught, then partially coherent, and if it is very more than very large than your T naught, that is the wave packet dimension, time distance, the time duration, then it is coherent wave, right? Now when we talk about helium neon laser, that is the light source having a time period of 2 times 10 power 2 times 10 power minus 15, that is in order of femtoseconds, but the time period of the detectors that we use are in order of microseconds, right. So we introduced one more parameter known as average of your actual wave packet. So instead of actual wave packets with significant fluctuations, we actually use average intensity and temporal average, right. So we define how to define average intensity, and then temporal average intensity, temporal average of the function over the time delta t, right. And then we discussed, if you want to, we discussed that coherence actually have two ways of defining coherence. One is temporal, another is spatial. When you talk about temporal, you actually compare with the same function or same electrical field or same wave packet, right. It's like comparing apples with apples, not apples with oranges, okay. So now or apples with another apple, one apple with the same apple with different time instance, right. So so we try to understand what is the delay. So we first define what is mutual coherence, that is for two different electrical fields or two different wave packets. Then we define for autocorrelation with the same wave packet. So what are the assumptions for the same wave packet, okay. And then we found out what is the mutual coherence function, and from there we talk about how to normalize the mutual coherence function, because usually we use only those functions which is having the maximum values of 1, right. So we also need to normalize our functions. So we use it, and then we define something known as small gamma of tau, and then we actually define it over here, and that's actually known as complex degree of temporal coherence. Now this small value, small gamma of tau of the delay will be used to define the coherence time, that is tau c, that we will talk about in the next session. Thank you.